We're going to continue talking about Fourier transforms, but now we're moving on to the discrete Fourier transform. And so what we're looking at now is discrete signals. We've just spent quite a bit of time talking about continuous signals, and we want to talk about how this is similar, but what are the differences between a discrete representation of the Fourier transform. So the discrete Fourier transform is largely the same, right? We're going to expand in terms of these exponentials, complex exponentials, just like you would in a normal continuous time case, except for the fact that one of the things we know about discrete signals is they repeat themselves over some interval of, let's say, frequency of 2 pi. So you're going to get this repeating pattern in the frequency domain, and it's very different than the continuous Fourier domain, where as you go to higher frequencies, you just add higher and higher frequency content to your signal, whereas here it repeats itself. And that's one of the major differences between the continuous time and the discrete time Fourier transform. So let's take a signal here. This is a discrete signal. It's 0 everywhere until some negative n1, where you sort of have some shape here until n2, then 0 again. And so what we'd like to do is represent this signal now in the Fourier domain. So this signal is x of n, and we're going to approximate it with some x tilde of n. So x tilde of n is the approximation of this signal here in the Fourier domain. And the way, of course, we're going to do that is expand in terms of a bunch of exponentials here, right, with a fundamental frequency 2 pi over n. And we're going to add up all these modes to create the signal that you see here. And of course, there is a way to compute these AFK. But notice the one thing that's important here. Once you've committed to this, and you're going to expand in terms of these essentially what are sines and cosines, this signal is periodic over some fundamental period. So what's going to happen is when I represent this discrete time signal in any actual application, it's going to be a repeating pattern. So here it is. Here is your basic signal with some n, which is sort of your period that you've chosen for this, and this pattern repeats itself in time, so it's periodic with a period of n points. And of course, this n has to include negative n1 to n2 if I want to capture the signal correctly. But remember, this is a representation or an approximation to the real signal, which is here. And now once we go to the Fourier domain here, I have this periodic signal that you're seeing here because I've committed to using these cosines and sines, which are these complex exponentials. So let's talk about how to compute the coefficients in this representation, because actually that's where the work is. We have this approximation to the signal. Here it is. And so you have the Fourier modes you're going to use, and then you just have to say for a given specific signal, well, how do I compute the coefficients of each of these Fourier modes, the A of k? And of course, we already done this with the discrete Fourier transform. Here is this representation. It's 1 over n, where n is the period, right, of this discrete signal. And you're going to sum over a total of n points. And usually you just pick the easiest and most convenient n points to make this period. And you take this signal, you project it into the Fourier modes, and this is how you can compute the A of k. So this is the idea, is the summation over the Fourier modes and computing these coefficients, which allows you then to estimate or approximate this signal in a Fourier decomposition. And again, the implications of it is that you're going to create periodic signals like you're seeing here over time with some period n. So we can start to look a little bit closer at this, and we're going to start building some representations up that are going to be nice for us to use. So we look at this signal here. We see that the A of k are given by this 1 over n, the signal x of n that you're trying to approximate, times this Fourier component. And so now here, if you look at the signal above, it's going from negative n1 to n2. So now I'm going to look at this as I take this n to be quite large, or as I take n to be infinity. In fact, if I do that, then here is the representation of this signal. So I can just expand this out from negative infinity to infinity, this signal here. And of course, the x of n only has a finite number of points. So when I go to negative infinity to infinity, I haven't actually added anything to the A of k's, okay? because all the signal is 0 out here and 0 out here. So this is my representation for the A of k. And what we're going to do with this is we're going to define this summation here, the x of n e to, so we're going to define this quantity here, x of e to the I omega is negative infinity infinity, x of n e to the negative I omega n. So you take your signal, multiply by a Fourier component, and you're going to sum this from negative infinity to infinity. This is like your, essentially your coefficient for each of the modes that's going to come out of this. In fact, we can use this then terminology to represent the signal here. So if we have this here, this definition that we're going to use, which is the signal multiplied by the Fourier component, integrate over the whole thing, then the A of k, each component for the kth component is 1 over n times this x e to the I k, and now we're using omega naught. And omega naught now, remember, is the 2 pi over n, which is the period of this signal. So this is a convenient representation. In some sense, it's like representing the Fourier coefficients like we had before in the continuous case. That's what we thought about as the A of k, but now that's essentially the role that this is playing here for us in the representation for the discrete time Fourier transform. So if we look now at the representation then of our signal x tilde, this is the approximation to the full signal, is the finite sum over a finite number of n. Remember, n is the number of period points. 1 over n, this coefficient here that we compute, which is again the sum over that signal, times each of the Fourier components. So essentially this is a normalized version of the Fourier coefficient of the A of k, where 1 over n is taken out. And here remember that omega naught is 2 pi over n, so this is your fundamental frequency. So again, once you've moved into the discrete time case, we have to take into account the fact that we're no longer, integrating from negative infinity to infinity or summing negative infinity to infinity. We're summing up over a finite number of n in an interval. And so we have it right here in this representation. So one thing to recall is that, you can basically rearrange this formula here to find 1 over n is omega naught over 2 pi. And look, there's a 1 over n in this formula here. And we're going to replace it now by omega naught over 2 pi. And so you'd get something like this. So you have a scaling factor of 1 over 2 pi. So in some sense, we're going to scale this down to, one way to think about it is a 2 pi domain. In fact, all the fast Fourier transforms that we normally would work with are always making the assumptions that you live on a 2 pi periodic domain. So even if your period is something else, you have to have a scaling factor, and this is sort of in some sense that scaling factor, 2 pi over n. N is your actual period, but 2 pi is the period that you're going to be working with these Fourier modes. So once you've done this scaling, you have 1 over 2 pi here, you have the Fourier coefficient, and then you have your actual Fourier mode that you're working with. This is just the weight of this Fourier mode times omega naught once we've scaled into this coordinate system. So a pictorial of this representation is something like this. I have a signal here. We're looking in the Fourier domain. And in the Fourier domain, what you're seeing here is it's a repeating pattern, right? So we're looking from negative pi to pi. That's our interval that we're going to be working over. Remember, it's a 2 pi domain, and normally we just think about, I can take any 2 pi signal, but I'm going to take it from negative pi to pi, so there it is. And this is the signal. It repeats itself. And what you're looking at here is, this is omega naught, and we're going to basically, this is the frequency you have here, and then you have the height of this thing here, which is the Fourier coefficients times the actual frequency it's at. So this is one way to sort of think about the representation of moving in and out of the Fourier domain in the discrete time manner. So just to summarize, here is sort of your boxed formulas, the ones you have to really know, which is what you're looking at here is how to get into the Fourier domain and how to get out of the Fourier domain. So if you give me a signal, x of n, and I want to move it into the Fourier domain, I take that signal x of n, multiply here by e to negative I omega n, sum from negative infinity to infinity. And that gives me these coefficients x, which are essentially the spectral or the frequency representation, the weights of the frequencies in the Fourier domain. If you want to come back out of the frequency domain, then you take those components and you integrate against e to the I omega n over all frequencies from 1 over 2 pi. And actually the frequencies, sorry, not all over frequencies, any 2 pi bin that you're looking at. Remember, everything lives in a sort of a 2 pi bin, and it repeats itself in the frequency domain. And that's one of the characteristics of the discrete time signal versus the continuous time. So this formula is super important. It's the one that you use to basically do the discrete time Fourier transform. And in some sense, it's the one that essentially gets used when you do a fast Fourier transform. A fast Fourier transform ultimately assumes that you have a signal which has a finite number of points, n. And then what you're doing is you're going to think about that finite number of points being on a 2 pi periodic domain. Here's how you come in and out of the Fourier domain. This is a very important formula. It is the map to get in there and come back out. And remember, the entire goal is once I'm in that space, I want to do some advantageous manipulations of my signal and then come back out, because the Fourier domain is a fantastic domain to do signal processing in. All right, so let me just show you a couple signals here. These are just signals that we can put in here. Here's a signal x of 1, and this is sort of a long spatial extent signal. And if you were to Fourier transform this, here's what it looks like. Something like this has like a tent type function here. And again, it's a repeating pattern on every 2 pi. So, which is exactly what you expect. So in the Fourier domain, whatever lives on the interval negative pi to pi just repeats itself in both directions, which is again different than the continuous time Fourier transform, which you don't have that repeating pattern of what you see here. Here's a second signal, slightly different, and this is what you get here for its Fourier transform. Notice here, now you're still repeating on the interval, but negative pi to pi looks quite different. Everything gets shifted over by pi in this signal here. So these are just representations of the discrete time Fourier transform, and it'd be helpful to do an example just to kind of show how this works out in practice. So what we're going to look at here as a signal, x of n, is a of n, u of n. Again, this is a signal that comes on at n equals 0 to a value of 1. And we're going to assume that a is less than 1. Otherwise, as we iterate forward, this thing will blow up. Okay? So we're going to take a less than 1, and we're going to work this out. And here's what it gives for us. So first of all, we're going to compute our Fourier coefficients, or the Fourier representation of this, which is this x e to the I omega. It's equal to, well, just put in your signal x of n, which is a of n, u of n, e to the negative I omega n. But notice u of n is 0 until n equals 0. Then this is 1. So I can just replace this by a sum from 0 to infinity a of n, e to the negative I omega n. Notice that this is to the nth power. This is to the nth power. I can pull it out and have this common representation here where the two terms are together, both to the nth power. So this is the manipulation we do, and this helps us because now once we have this representation of x e to the omega is this sum where I'm going n to 0 to infinity of this quantity to the nth power. This is actually equal to, because of a geometric series, 1 over 1 minus a e to the minus I omega. In fact, if you recall, this is your geometric series here. 1 over 1 minus x is 1 plus x squared, which is exactly what this thing is, where this is x. So this is how this all collapses into this very simple and very nice formula for us to use, provided, again, that that a is less than 1, which it is. We assume that. So this is a very nice, simple example. And this kind of example then would show up also in a discrete Fourier transform table. So in the book chapter, there is in fact a discrete Fourier transform table that is given, and it allows it computes a bunch of these very nice transformations like this one here. It puts it there, and so you can use it for future. Okay, let's move on to a second example. And here's the second example, which is we're going to take an infinite signal like this, which is 1 for some negative n1 to n1, 0 everywhere else. We're going to Fourier transform it, do the discrete Fourier transform on this. And so again, we can just basically throw this directly in to our formula here. And this sum was from negative infinity to infinity, but of course it's 0 outside of negative n1 and n1. So this sum just collapses down to this representation, which you can work out and show that it in fact is exactly this here. You can actually do this finite sum very nicely, and this gives you a nice representation of what the Fourier transform looks like for the step function, which is something like a sinc function. Okay, and we've already seen the sinc function before for the continuous time Fourier transform, but here it is again now for the discrete Fourier transform. All right, so there's the pair. There is the signal. Here's its Fourier transform. It's like a sinc, but notice the big difference here is that, again, it's a repeating pattern from negative pi to pi. So here's the basic signal, so it's part of a sinc function, and then it repeats itself. So you should remember that is that everything in this discrete time Fourier transform, whatever interval of 0 to whatever 2 pi interval I pick in the Fourier domain here, it just repeats itself. And that's the characteristic feature of a discrete time Fourier transform. All right, let's continue on this and start thinking about Fourier transform of periodic signals. All right, so here is I'm going to show you the simplest periodic signal. It's just the complex exponential, right? This is cosine and sine, so it's cosine omega naught n plus I sine omega naught n. So this is a very simple signal to think about. And you can ask the question, what's the representation of this in the Fourier domain? Well, in the Fourier domain, a cosine or an exponential like this is actually a delta function. So we've already done this example before, but the way to think about it is the representation then in the Fourier domain is just 2 pi delta function omega minus omega naught. So this sifts the value out of this function at e to I omega naught n. So if you plug this into the inverse formula, you just get back here. And we've added this factor of 2 pi p. And the reason we do this is because, remember, this pattern repeats itself every 2 pi. So I can pick p equals any integer, and I get exactly the same thing that I had here. So another way to look at it is, its Fourier transform is this function here, which lives over the entire frequency domain. So you have the sifting property at omega naught, and every 2 pi you get the sift property again, plus 2 pi, minus 2 pi, minus 4 pi, plus 4 pi, and so forth. So remember, here's your repeating pattern. And of course, normally, all you care about is some domain from negative pi to pi to be looking at. That's the domain that matters when you start to represent a signal generically. But technically, in the Fourier domain, you get this repeating comb, if it were, of a pattern in the Fourier domain. Let's do one more example of this, which is our Fourier transform of the cosine. So we take our cosine, here it is, x of n is cosine omega naught n, which of course is 1/2 e to I omega naught n plus 1/2 e to minus I omega naught n. And so what produces this in the frequency domain is a delta function centered at omega naught. And what produces this other one here is a delta function at negative omega naught. So essentially I have a delta function of strength 1/2 and another delta function of strength 1/2, and here they are. These two spikes here are the 1/2 and 1/2, and this makes up the cosine. But of course, since we're looking at a discrete time signal, this pattern repeats. There it is again, there it is again shifted by 2 pi. So this is kind of the implications. You just have to keep that in mind, that once you start working with a discrete time signal, you repeat yourself in the Fourier domain, which you don't do in the continuous time representation of the Fourier transform. So let's talk about some of the basic properties, because I want to make sure we understand these. They're almost all the same as you would get in the continuous time Fourier transform. So I'm just going to outline some of the major ones. And the most important one, again, and this has always been holding for us for LTI systems, Fourier transforms, Fourier representations, is linearity. So if you have a signal, x1, it has a Fourier transform, capital X1, Fourier transform x2 to x2, then if I took the Fourier transform of ax1 plus bx2, it is a times Fourier transform x1 plus b Fourier transform of x2. Okay, this is one of the most important properties, and of course it holds because integration, which is what the Fourier transform is a linear operation. So this is one of our most important properties. However, there's others. There's periodicity. Again, here is the periodicity. You shift this by 2 pi, you get exactly what you had before. That I've already shown several slides of this previously, that this is exactly what happens in all these signals. And then so that you have that, you have also the shifting property. So if you shift this by some n naught points, then you just get a phase factor out front of the signal, unshifted signal, shifted by e to the negative I omega naught n. Same thing here, you can multiply the signal by some phase factor and shift it in the frequency. Okay, so the shifting properties are very nice. You just get a phase transformation. You also have conjugation. So if you take the conjugate of the signal, it's equivalent to the conjugate of the Fourier domain with, now you have an e to the minus I omega instead of e to the I omega there. So these are some of the properties that we would commonly work with. And so what you see here is we have the discrete Fourier transform, which has very much what we want to think about is that when we take the discrete Fourier transform, we just have to keep in mind that we're now working with a finite band of frequencies to represent a signal. And that band of frequencies repeats every 2 pi, as I've shown in these examples here. And so unlike the Fourier transform, where we always have to worry about convergence by summing up over an infinite set of Fourier modes, here we have a finite band of Fourier modes, and they repeat themselves. And so we have usually a lot less concern about whether this will converge or not. Normally what you're going to do, though, is take a finite domain, and the fast Fourier transform, one way to think about it is you're going to pick a finite domain, you're going to scale it to 2 pi, put yourself in the Fourier domain, do your operations, and come back. So this is a very nice architecture for doing exactly that. So more properties of discrete Fourier transform in the next lecture.